Okay, welcome back, and we are going to continue yesterday's lecture about representing paths of polynomials and then trying to solve the k-path problem in randomized 2-power k time. Okay, I hope we all agree that the broad idea is to reduce the path, reduce the graph instance to a polynomial which has the property that the polynomial is identically 0 exactly when the graph, the typo remains, the graph has no paths of length k. Okay. All right. So, so the idea is that you do this translation and basically feed this into a polynomial identity tester, which is really simple. So, you start with a graph G and come up with some polynomial p. Okay. Hopefully, you come up with a polynomial that you know how to evaluate easily. And then you evaluate it at some random vectors. If all the evaluations turn out to be 0, then you declare that it is indeed the 0 polynomial with high probability. If at least one of the evaluations turns out to be non-zero, then you know that it is not the 0 polynomial, which means that you actually have a path of length k, and this conclusion you come to with probability 1. Okay. So, the goal is to first of all come up with a polynomial that preserves the semantics of the existence of paths of length k. That is goal number 1, and goal number 2 is to make sure that you can actually evaluate this polynomial efficiently. Okay. So, it is going to be challenging to talk about evaluation of a polynomial without having the polynomial at hand. So, let us just go over how we constructed this polynomial yesterday, okay, and we will recap this. So, hopefully, it will be clearer today as to why we did what we did. So, let us start with an example. So, first of all, we are building a polynomial where every monomial corresponds to a walk. Okay. Somehow our vague psychological intuition is that walks are computationally nice. So, let us work with the space of all walks, and maybe if we do this, somehow the evaluation will be doable. Okay. So, that is just a very vague intuition at this point, I admit. Maybe there is a better way of doing it, you would go back and forth, but let us just understand this picture completely, and then we will see if we can simplify it offline. Okay. So, for every walk in a graph, this is an example walk, it repeats the vertex b. It is a walk that happens to be a serious walk, it is actually repeating a vertex, but every path of course is also a walk. But in any case, for every walk we are going to introduce a monomial, okay, which just has a variable for every vertex in the graph, and it is just the product of all the vertices. It is the product of all the variables corresponding to the vertices that participate in the walk. Okay. So, in this case the variables, the vertices participating in the walk are the vertices are a, b, c, d, e, and you have the corresponding variables listed out here, okay, with the repetition. Okay. So, every occurrence of the variable in the walk corresponds to a monomial. Okay. Now, every path is going to lead us to a monomial, every walk that is not a path is also going to lead us to a monomial. Okay. What we would like to encode is that walks that do have repetitions somehow cancel out among themselves. Now, this is not happening automatically. If you have these monomials, you have no reason to believe that the structure of the walks in the graph is such that they somehow magically cancel out. So, we will have to do something more to ensure that they cancel out. So, what we did yesterday was that we made several copies of these monomials, and with each copy we gave a labeling. Okay. So, for every so these are all walks of length k, remember. Okay. So, these are all monomials with k variables. So, we essentially made copies of these monomials, but for each copy we now have a second coordinate which corresponds to a permutation on k. Okay. Now, what happens is that if you have a repeated vertex, for example, we have b out here. So, consider any fixed labeling, okay, where the first occurrence gets labeled 2 and the second occurrence gets labeled 5. There is a unique partner labeling where these two labels are swapped. That is this one, where b gets 5, the first b gets 5 and the second b gets 2. Okay, and these two labelings cancel because we are going to evaluate these polynomials over fields of characteristic 2. Okay. So, when you list out everything, all the monomials corresponding to a walk with a repeated vertex, all of these guys are going to cancel. Okay? So walks definitely cancel. Is that clear to everybody? Yeah, with this proposal of monomials. What about paths? We need to make sure that walks definitely cancel. We also need to make sure that if the poor graph did have a path, somehow these terms that we have generated corresponding to the paths do not cancel. Okay? We don't want a polynomial that's identically 0 when the graph does have a path of length k. That's the only part that we are sure about. Let's try to preserve those semantics. Okay, so clearly within a list of monomials, let me just be lazy and go back. Yeah, within a list of monomials, if this guy was a path, you didn't have the repeated vertex. Let's say the second b was some b prime not equal to b. These guys among themselves don't cancel. That's easy to see. Okay, because if there were terms that were the same, that means that the labeling was not a bijection. Okay. That's something that we worked out yesterday. That's definitely clear. But is there something else that could be potentially dangerous? Right. If you have, remember when we were doing the DP yesterday, we said that you can have multiple paths on the same vertex set, but it's just that they go in a different order. Okay, and here we are generating these monomials for every walk, meaning for every sequence of edges, every valid sequence of edges. We did not say that if the vertex sets are the same, don't generate multiple monomials. Okay, so for every valid walk, we have a collection of monomials. So in particular, if you have a path that's like this and another one that's maybe like that, that uses the same set of vertices, you're going to have two sets of monomials for both of these paths, but there is nothing that distinguishes them in our construction so far. Okay, so you may have two different paths in the graph on the same set of vertices. In particular, if you have an even number of paths on the same set of vertices, then all those cross terms will become exactly the same. You'll have the same list of terms for all of these paths. Now they're going to horizontally cancel. Okay, because of the same, so the characteristic 2 business is sort of a double-edged sword. It can cancel out things that you don't want to cancel as well. Sorry. Remove the badge. Okay, all right. Okay. There's a glare, I suppose. Okay. All right. Okay, now I can say whatever nonsense. It's okay. Yes. They are differing on the edges, the sequence of edges. Yeah, but I have not introduced them yet. Right? This is all that I've shown you so far. Right? Okay. So if you just use these set of variables, then it's not going to be enough. Right? Because somehow a lot of other stuff, other potential cancellations may happen, and you may potentially start with a graph which does have legitimate paths of length k, but the polynomial turns out to be the 0 polynomial, which is something that you definitely want to avoid. Okay, so that's sort of why. Okay, so that's sort of why we had this business about introducing variables that correspond to the edges as well. The path will cancel out with the reverse path. Yeah. No, yeah. So these are so every path, whether the graph is directed or undirected, the walk is a fixed sequence of edges, right? So for the sequence, you have variables in that particular orientation. Yeah.
So for every edge, you have a 1, 2, and a 2.
For every edge, I have a 1, 2, and a 2, 1, but here I will use the 1, 2 because that's the sequence in which you give me the walk. Okay. So let's say we're talking about directed graphs here. So I mean, and it'll work for undirected graphs because in an undirected graph you can orient every edge both ways, and the semantics of the path will be preserved.
If in an undirected graph you can just have one variable for each edge.
You can have.
The reverse path that he's talking about, it's actually the same path because in an undirected graph you don't have anything for the edges.
Well. No, so the thing is we are listing out every walk. Every walk is a sequence of edges. So if you have an undirected path, you can list out the walk in both directions. And its point is that if you don't use two sets of variables for the edges, then these two things might cancel. Let's say you have the entire graph is just one path of length k. Okay. What is a walk? We define a walk as any valid sequence of edges, meaning consecutive edges have a common vertex, right? So you can go from edge to edge to edge to edge, okay? So you have two walks in this graph, one going this way, one going that way. So these are two valid sequences of edges, even if the graph is undirected, okay? So if you do not, for every variable, for every edge, if you don't keep two versions, so if this is an undirected graph, then implicitly you think of it as having two directed edges. For each directed edge, you will have one separate variable, which you will use depending on which direction you are walking in. So these two terms will not cancel. Okay. So that's why we started off by saying let it be a directed graph. For every oriented edge, you have a particular variable. But obviously, it works just as well for undirected graphs. In fact, for undirected graphs, you can actually save and get faster algorithms, but that's getting ahead of time. Okay. Fine, so this is why we had the polynomial that we chose to have yesterday, okay. These guys sort of guard the paths, keep them distinct and prevent them from cancelling out across each other. These guys ensure that the walks definitely cancel among themselves. So if you had a graph which had no paths of length k and only had walks of length k, then these guys would be responsible for making it the zero polynomial. If you had at least one path of length k, then together with these guys, you would have surviving terms. Okay, is that clear? Okay, and remember that it's important that you're evaluating this over a finite field of characteristic 2. Not get into the details of what the field is. It's sort of for the purposes of our discussion, it suffices that such fields exist and that you can use them. Okay, all right, so let's move along to evaluating this polynomial. This, on the face of it, is a huge polynomial. The variables that we have to deal with, the answer, this is still not clear somehow. For every vertex in the graph, we introduce k variables, v1, 1, whatever, sorry. How do I do this? V comma 1, v comma 2, v comma k. It's these variables that just keep getting rearranged. For every edge in the graph, uv, we have one variable which is, what did we call it, x, whatever, xuv essentially, whatever, x. So this is a particular walk that's v1, v2, v3, v4 up to vk. So that's why the notation is like this. But essentially for every edge, there's a variable that you can call upon. Okay, so you need the edge variables to work there. This is still not clear. So here, for example, you have k factorial permutations, right? But for each permutation, you just call upon the variable with the label that you need, right? So you need altogether the number of variables that you use is k times n plus n. Okay.
Each is a permutation of the one of the first one. Is that how we should?
Correct. So you start off with just YA, YB, YC, YD, YB, YE, but then you have for all permutations from k to k, you make a copy of this monomial and basically impose that permutation on it so that it becomes a distinct monomial on its own right.
Right, so that's the kind of a subtle point, because these resulting strings need not represent a valid walk.
No, you always start with a valid walk.
You start with a valid walk and from then you apply the permutations that you described and then you get a series
Correct, but
of
if you
strings, all of which may not be a valid walk.
well, if you just focus on the first coordinates, they're exactly the same for all of these monomials.
True, then it means that if they were to be a valid walk, they mean that they start with the same starting point.
Right, so the labeling doesn't signify the order of appearance of variables on the walk. It doesn't signify anything. It's just a hack. It's a hack to ensure that terms cancel when they're repeating vertices. So there are no semantics associated with the permutations. Okay, the permutation it's just a trick. I mean, I guess if you were doing any bijective labeling would work. Yeah, absolutely. You could, you could label it anyway. I mean, yesterday, in fact, I had colors, but I thought that confused us more, so I just stick to labelings here. Okay, so
what is the key here?
it's the length of the walk.
The original problem was we are looking for
Paths of length k. Yeah. So we are dealing with k path. That's the problem. You want to find a path on k vertices. Yes. Okay. So essentially, this is the structure of the polynomial, and here's the approach that we are going to take to evaluate it. Okay. Once we know that we can evaluate the polynomial in FPT time, in fact, we will see that you can evaluate it in something like 2 power k time. Once you can do that, you're done, right? Because then it's just a matter of doing this enough number of times for you to be confident about the identity testing business. Okay. All right, so here's essentially the polynomial. For every walk and for every labeling, we had this big term. Okay, we had the product of all the vertices, product of all the edges with that particular labeling. Vertices with that particular labeling, and then all the edges participating in the walk. Okay, so that we're going to use alpha WL to denote that big term. Okay, and what we're going to do is focus on just this part. I mean, I know that this sum looks like a big sum. Okay, overall walks, we said that this is potentially n choose k many terms. But for now, we are just going to focus on this part. And what we are going to do is use inclusion, exclusion to simplify it to something. Okay, we'll figure out what this part is and how it works out, but we'll simplify it to something where apart from this junk, you're actually summing over all subsets of k. Okay. After this, what you can do is you can interchange the order of summation. So this guy goes here, this guy comes here, and the rest of it stays as it is. Then for this part, okay, we are going to use dynamic programming. Okay, and this dynamic programming will be polynomial time. Okay, and this sum out here is how much time? 2 power k. We are doing something for every subset of k. So that's 2 power k dynamic programming runs. Okay, and so the walks is sort of been absorbed into something here that's convenient. Okay, that's what's happening. Okay, in case this was totally mysterious, I guess it's still mysterious, but this is what we are going to do. So first we'll do inclusion, exclusion to simplify this part into something that works in the context of DP.
Second summation, what is this X subset of K?
Mm-hmm.
What is it? L is a typo before that.
Oh yeah, L is a typo before the copy paste. Sorry, that's just X subset of K. Everywhere. I guess that must now be everywhere. So X subset of K is just X subset of K. Thanks. Okay, so like I said, we'll focus on just the first part here. Okay. So we are concentrating on this product summed over all bijections. Okay, and somehow it's not completely clear how to computationally restrict our attention to bijections. I mean, of course, there are only k factorial bijections, so you could potentially work this out. But if you flatten it out like that, then there is no utility when you patch it with the walks. Okay, because when you patch it with the walks, then you have a big multiplicative factor with the walks, with the collection of all walks. Is there a question? Okay, all right. So we're going to try and sort of break this up into something a little more convenient. And this is going to be using, again, inclusion, exclusion. We're going to do inclusion, exclusion over the space of bijections. Okay, so in the first step, let's consider the following universe. This is the set of all functions from k to k. Okay, we ignore the bijectional aspect of the functions. Okay, remember what we did with walks and paths? We said, okay, paths is what we want. walks is a superset of paths. They have the paths and they have some other junk. So let's look at the set of all walks and then do some circuits to bring out the paths from the walks. Okay. Similarly here, bijections is what we want, but this is our haystack. Okay. This is like all possible functions from k to k. Okay. Now let's define our sets as all, let's say ai is all those functions where I has an inverse. Okay. So I is an element in k. For every I in k,
I is a function.
no, I is a fixed element from 1 to k. So for all, maybe I should have written that down. So for all I in 1 to k, you define the set ai as just focusing on those functions where I gets an inverse. Okay. Sorry? I is in the image, yeah. Yeah, I is in the image, yes. Draw a picture. So looking at functions from k to k, I'm saying that there's some guy here, there exists some j that maps to I under the function f. Okay. I'm not focusing on permutations, I'm focusing on functions.
So is it exactly one, should the inverse be a single or that be?
I mean, these are still functions, right?
Otherwise, yeah, how can
You cannot have two guys mapping to one.
I is the image. I is in the image of the function.
Okay, yeah, okay, sure. Yeah, I mean, I just want that there is somebody witnessing I. Somebody witnessing I. I don't care if there are many guys witnessing I.
Technically, where I has a pre-image, right, not the inverse.
Yes, I is the pre-image in the function.
Yeah, okay. All right.
It having an inverse.
Whether there would be a set which is mapped to I, right?
I is in the image.
I is in the inverse. Yeah, fine. I has an inverse, it's in the inverse, whatever. You guys understand? Potato. Okay. All right. So there's some guy, so you're collecting all functions where the function chooses to map somebody to I, at least. Okay? That's what you collect. Fine? Okay. All right. So what's this guy? Intersection of ai, again that's a bad typo, sorry. Intersection of ai, I going from 1 to k. Permutations. Right? So if you insist that every guy has somebody mapping to it, then you get precisely the bijections. Correct? And this is really what we want to count. Okay? Now let's sanity check this expression. Here on the left, you have these big monomials, okay, and here the AIs are these sets of monomials, okay, and for the purposes of inclusion exclusion, I'm looking at the cardinalities of those sets. So what do you make of this expression? Correct or wrong? Okay, how many say wrong? Okay.
Cardinality sign should be outside intersection.
Even if it's okay, cardinality, even if it's outside the intersection, is it still correct? What do you have on the left hand side? What's the object on the left hand side? What's the nature of the species on the left hand side? It's a polynomial. What's the guy on the right hand side? It's, yeah, I mean, depending on how you do it, if it's like this, yeah, sorry, the cardinality should really be on the outside. So it's an intersection of a set and I'm counting the number of elements in it. So the guy on the right is a number. So you have a problem. Okay, so we're not going to work this out precisely like this, but I mean, hopefully you're getting some intuition for the idea. We're trying to sort of wade around in the space of functions, okay, and we're trying to zero in on the bijections, okay, somehow. And now what we have to do is just some math. let's just define the universe to just be the space of functions, and let's define the weight of a function to be this monomial. Okay, and then let's say that ai is those functions where I is in the inverse or whatever it is. Okay, and so the weight of a set is going to be the sum of the weights of the individual elements. Okay, now how about this? Is this better? Is it at least type checking? So here you have all those guys that correspond to bijections. Okay, you have all those guys that correspond to, so you just have pure functions that correspond to bijections. For every function, okay, you're now going to, so what is the weight of a set? It's the sum of the weights of the individual elements. The weight of an individual function is this guy. Okay, so it's going to turn out to be exactly the same thing. Sorry? This was a monomial, yes. You mean you're used to weights being numbers? Is that your point? Doesn't hurt, right? I just defined the weight of the function to be a monomial. Okay? All right? And this is something I'm not going to do because it's really too boring, but it turns out that if you define weights on a space where addition, etc. is sane, okay, as in it's commutative and all those nice things, the inclusion principle, inclusion-exclusion principle works in exactly the same way. Okay, so you actually get, oops, something like this.
When you say the weight of function is a monomial, what does it mean? If L is not a bijection, then what is it that you get?
Well, it doesn't matter, right? The monomials, I'm free to label them with whatever label I want, right? Yeah, it's just that all the monomials that don't correspond to bijections will magically cancel because you're doing inclusion exclusion. Okay, so all the ugly functions cancel and the inclusion exclusion formula. Yeah, correct. The labels that you get, you're free to label the monomials with whatever function you like. When we wrote down that sum, we insisted that we only loop over functions that happen to be bijections because that's what we wanted for the cancellation property and so on. Okay. Fine. Okay. So this is what we have, and to be honest, I don't know what exactly the next slide is. Let's see. Okay, sorry. Let's understand this. Let's understand this quantity here. What is, so again, remember that when we were doing Hamiltonian paths, so Hamiltonian paths for inclusion exclusion is a classic simple application that's always worth remembering and going back to and drawing analogies with, so you know where you are in the process. Okay, so in Hamiltonian paths, when we had this term, okay, forget about all the other junk because that's easy to do. Okay, when you had this term, you said, what was it? It was all the paths that avoided all the vertices in the subset Z, right? All the walks that avoided everything in the subset Z. So we said throughout Z of the graph, Z from the graph, and count the walks on the remaining graph. Okay, so what's the semantics of AI complement here? What is AI? Functions where I has an inverse. AI complement is the set of functions where I doesn't enjoy this status, meaning these are functions that somehow avoid I, right? Okay, and here's I, and you're looking at the class of all functions that choose to like dump I. Okay, they're ignoring I, they're mapping everything else to somebody, but they're not mapping I to anything. What's the intersection of AI complement over I and Z? Now I have a subset Z, and these are all the functions that neglect Z. Let's say that, okay, I'm not going to map anybody in Z. Okay, so these are functions that somehow have an issue with Z, so they don't map them anywhere, they map the rest of the guys wherever. Okay. Yeah, X is this quantity on top. Yeah. This is, I mean, yeah. This, forget the X. It's exactly this expression. Okay. That's the weight of u. Okay? Yeah. Good catch. Okay, so these are all the all the functions that precisely avoid z, meaning that they map. So these are, now you're summing over functions. So when you're trying to evaluate this guy, right, intersection of I and z, ai complement, your sum is over functions that whose domain is what? K minus. No. I'm asking for the domain. I'm saying that if you're only trying to understand the functions that turn up here in this context.
But this seems that z is not in the range, right? Because
No. I'm talking about I not having an inverse, right?
So z is not in the range.
Okay, sorry.
Z is any subset.
Yeah, that's in this side.
Okay, sorry. Just a sec. What did we say? We said that I doesn't enjoy an inverse. Actually, it doesn't matter how you look at it, right? Because these are bijections. I doesn't, no. 1 second. No. So for a bijection, I mean, everybody is uniquely matched, right? It is symmetric, right? When you're trying to capture bijections.
It's not bijection because AI is.
No. It's.
I is not in image.
So if
Yeah. I'm saying.
projection, I will always have an image.
Correct. So I'm saying that. I'm just saying it doesn't matter whether you try to concentrate on. I mean, how do you capture the space of all bijections? Whether you say that I doesn't have an inverse, or whether you say that I is indeed mapped to something.
Then it's not set of all functions, set of all maps.
Set of all maps.
Okay,
Set
fine.
of all onto
Fine.
maps. It becomes clear.
Okay, yeah, okay, because you're then having to look at relations. Okay, all right. So let's just try to get the semantics of this correctly then. So the sets. So this is. So all the i's in Z are not mapped to anything. So K maps to outside of Z, right? That's what's going on. Okay, all right. So this is all functions L that maps K to K minus Z, right? K minus Z. But then I have an outer summation which is over what? It's over all subsets of K. Okay, just keep reading the N as the K. Okay, that's correct. Okay, so now because of symmetry, it doesn't matter if I'm mapping to K minus Z or Z, right? Because for every K minus Z, I also have a Z. Okay, so that's the expression here. This just should be the other way. K mapping to Z. Sorry about that. Okay, all those functions where K chooses to map only to Z. It doesn't matter how you look at it, right? If K is not mapping to Z, it's mapping only to K minus Z. And it's notationally easier for me to just say that K maps to Z. Okay, so K is mapping to a restricted range. Okay, yeah, thanks for that correction. Yes. Okay, so we have this. So basically, okay, so and the sum is over these monomials again. So what's happened is that I'm now looking at just a restricted set of functions that map not to all of K but map to some subset of K. Those are the terms out here. Okay, why did the -1 disappear? Guesses? Okay, A. Yeah, because it's characteristic too. Okay, thank God. I thought you'd say that's also a typo, given so many. All right. So yeah, you're looking at fields of characteristic too. So when does the minus sort of play a role? When two things are the same, this minus this becomes 0. Okay, but when two things are the same, that plus that also becomes 0 in a field of characteristic too. Okay, and this is all that you care about. Okay, all right. So you can ignore the -1 term. So this is what it's boiled down to. Okay, so let's pull this up. Let's go back to the big picture. So now we have, okay, I'm really sorry, you'll have to read this the other way throughout. It doesn't, is it? No, it's not. No, yeah, because I copy pasted everything, it can't be correct. Okay, all right. So, so you're looking over a restricted class of functions. So for all subsets of K, you're looking at functions that map only inside that subset. Let me just maybe put the correct version on the board so that it stays. So you're looking at subsets of K, and your next sum is over functions that map K to this subset. And then you have some alpha blah blah. And of course there's a big sum over all walks. Sorry? No, this is actually alpha. I mean, in the calculation that we did, this was just the same as alpha. I was just bringing up the possibility that it might be something different, but it turns out to be just alpha. Okay. Is this fine? This is what we have via inclusion exclusion. This is exactly our polynomial. Now we swap the outer two summations. We take the W inside. We bring this out. Okay. And now, so for every subset, we have to evaluate this fellow. Okay. But now this is a lot like the Hamiltonian part dynamic programming that we did in spirit. Of course, there's a lot of notational nonsense. So we start here. We are looking at this. Let's just recall what this guy was. It was the product of all the edges and then the product of all the variables with the labels dictated by L. Okay, just in case we've forgotten by now, slightly. Now let's look at what this space really is. All walks. We're looking at all walks of length k. We might as well concentrate on walks starting at a particular point, okay? Because you can just sum over all vertices. Okay, so this space that you're summing over, W, can be broken up into the union of walks starting at particular vertices. So that's going to be another sum that's polynomial. You can forget about it. And for now, we can just focus on walks that start at a particular vertex V. Okay, all right. So now for the dynamic programming, let's define these intermediate guys. Is everyone able to see this though? These intermediate guys are walks of length d that start at a vertex V. Okay, clear. Again, this is something that we'll keep coming back to. This expression, the rest of it is the same, but here you're focused on walks of the form V1 to Vd, where V1 is equal to Vd, and then the usual plot. Okay, sorry? Yes, thank you. Someone's not sleeping, that's good. So walks of length d starting at V. So if a walk of length d is starting at V, what must it do? It starts at V and then does what? It goes where? To a neighbor of V, right? That's the next thing. So for dynamic programming, here's what we'll try to do. We'll try to go somehow from TVD to, we are going to say, well, this is going to be the sum over all neighbors of V, T of U comma D minus 1, something. Okay, so any walk of length d starting at V can be thought of again as the union of all walks of length d minus 1 starting at one of the neighbors of V. Okay, so that's okay. I mean that's just the global idea of the DP. You're going to try and separate out V from the picture, and then you're going to try and appeal to what are all the choices of neighbors of V, whatever some U are. And you're going to try and bring this down to these guys, because these guys you have already computed. Okay, this is a smaller quantity, right? UD minus 1. You want me to go back, or this is okay? Mm-hmm.
K to X.
K to X.
Sorry, it's the other way, yeah.
The point is that there could be two different functions which restricted to K.
Mm-hmm.
So since it's not the full, it's not mapping to the full thing. So
Well,
they might cancel. Because there could be two permutations whose first D part is the same, and the last part is different.
correct, but this will patch with, I mean, it'll patch correctly with something outside. I mean, even if you're pulling in something that cancels. I mean, let's go over it, and we'll come back to this and see if this is an issue. By the way, when you're looking at L mapping K to X, in this intermediate stage, you only have a path of length D, so you only worry about what the function L maps these quantities to. You don't care about the further. I mean, what it maps the rest to is not going to be important here. Okay, but you're still running over all possible functions. Okay. So all right, let's. Okay, fine. So let's just pull this out. By the way, you do have the edges as well, right? Will they cancel out as well? Even if the projections. Look. No, I think his concern is that when you project two functions to an intermediate value, even if they were distinct before, right, they may cancel out because their projections on the first D guys is the same.
Two paths.
Right.
Whose first D vertices are the same, first D edges, and then they diverge differently. So
Okay.
this partial solution,
Okay.
they will both give us the same.
They will both give us the same.
But we will not do modifier depending on intermediate step.
So basically you take
That's one way of fixing it. We don't.
Represented just
But then
once
you
in
have
this
exponential.
quantity.
Let's not. So okay, look.
These numbers.
Yeah.
You are
Look.
never going to do this. What are you going to do? You're just going to evaluate this.
Correct. So the guys cancel.
Like you're never going to do anything else.
See, the guys cancel only at the
You're
point.
storing it in some way, which is not this.
No, so
Yeah.
think that at every point of time, how do I start? Look, if I have a huge polynomial and I have to evaluate over circuit, right? I just put this, and at every point of time I make some simplifications, right? So I'm never going to write down this, right? So you came up with this variable 2, 3, 5, 7, 9, 8, 6, 4, 111. Okay, at every point of time, when I get this YD1K, this edge, okay, whatever this number is, whatever I have computed up until now, whatever the variable this is, I will multiply with this and I will get this number, right? This is what I will do using DP. And finally, what I will evaluate with mod 2 or something at the end. I will not do it. Only thing which you need to show that the size of the bits will not go. But if your field, you start with a field which is not too large, the size of the number which will grow in between the process is never going to be big too. So that's it. So you are never, you can never imagine to keep this huge, humongous polynomial ever in your life. It is just normal Schwarzschild lemma. There is a polynomial, okay? There's a big polynomial which is implicitly it looks like this. No, not even representation.
No, this
but
is just a
I do not
simple
even know how to evaluate that polynomial, right? So this is giving you method to how to evaluate this polynomial. If you tell me that this variable take, look, all you know that there are m plus nk variables, right? I start from a field and arbitrarily gave these guys these values. Okay, now I just want to evaluate what is this number which comes for this particular polynomial. Is it 0 or 1 with respect to mod 2? So I will add up everything and finally I will say, okay, is it odd or is it even or whatever, and do this mod towards it.
But you do this at the end,
Not at the
Let's
intermediate
let's
stage.
not do the intermediate step because intermediate stage is like, 4, 2 plus 5 is 2 plus 3, okay, now 0 something. That's not.
Yeah, that's
The
right.
point is just because we're going to have this simplification in intermediate step, that not blowing up process, you might actually lose some solution. We are trying to come count the number of k-length paths.
No, we are not trying to. We can never count k-length path in one
That's a
vector.
problem, right? If there
No.
is-
No,
I'm
we
just
only
asking.
care, we only care,
Just
we,
a part.
yeah.
Yes.
Okay, you're right.
Yeah, so we only care if the final answer is 0 or not. Yeah, so these guys at the intermediate stages, I mean, the evaluations will happen step by step. You're going bottom up, right? So you start with walks of length 0 or 1 or whatever you want to call it, a walk that involves a single vertex.
Look at this summation. So summation W V1 to Vd Y V1 blah blah. This inner summation I have already completed using dp. I just have, and Y V1 1 is some number 2, 3, 5, 7, 8, 100, whatever it is. I multiply with this. Then I another multiply with this. I get another big number.
That's not matter, it's a variable. It's a variable.
No,
Yeah.
but I'm only talking about substitution. I'm only talking about the number which I get after I have decided to put x v1.
Look, once we have identified a variable that's not inside any complicated summation multiplication, so we'll come to how this guy simplifies further. We don't quite have this guy exactly in the DP table. We will need a little bit of work, I mean maybe 5 more minutes of work, but basically you do the substitution once you've isolated a variable from the formula that doesn't depend on the rest. So you'll see that the substitution is quite clean. Once you do the substitution, like he's saying, don't do the mod 2 simplification right away. Hold on to those values, okay, and keep simplifying till the end, okay. You start with a field of size something like log k, okay, and you know, even if you blow up the size of the numbers that you're storing at every intermediate stage, at the end it's still some poly k bits, which is fine, okay, all right.
So that each term of these summation term is summation over L, all the functions from k to x.
Correct.
So, but we never use L of 1 in that term.
Why don't we use L of 1?
Is not used.
Here? In here?
Yeah.
Yeah.
L of 1 is not used.
No.
So when you change L of 1,
Mm-hmm.
the term remains the same, but you have a different, in the summation you have a different, you have two terms of the same, two monomials of the same, two identical terms.
Two identical terms, okay.
Which are added. So I'm just saying it should be k minus 1, set of k minus 1 to x and not k
Why
to
are
x.
you not using L?
Ah.
We are using L. Because y, v1,
Not
y,
using
y,
it
v1.
internally.
But you have taken that.
That's fine. I mean, you just loop over all functions and take the part that matters to you.
So all this
That's just-
cancellations are taken care by the inclusion exclusion.
Yeah, I mean, cancellations in terms of preserving bijections are taken care of inclusion exclusion. Cancellation in terms of cancelling out walks and preserving paths is taken care of by the structure of the polynomial. But sorry, I'm not completely following your question. Ah.
If I just change L1
Mhm.
and keep everything fixed,
Right.
then the second sum
Mhm.
is same, and so we are summing exactly.
The number of
exactly
terms in the first LHS is not equal to number of, in RHS has k times more, k plus 1 times more terms. See.
Okay, I mean, you would have to restrict this function appropriately.
K minus 1
Fine,
to x and
fine.
not k to x.
Fine.
It's very simple thing, but
Fine, fine, fine. Okay, fine. So, okay, so let me maybe explain this slide because we haven't really gone over it. So you're getting a little ahead of me as usual. But anyway, so here's the sum that we start out with. Okay, this is just the sum that we start out with. Nothing has changed. Okay, the line on the very top. Okay, so we are going over all walks of length d that start at the vertex b, and we are going over all functions that map k to x. Okay, and then you have this monomial. Okay, first thing I'm trying to do is to say that, okay, let me focus on all those functions that map the first element to 1, 2 up to k. Okay, so yeah, I mean, so okay, you're looking at functions like this. So this, I mean, this is a sum of a whole bunch of terms, right? So I'm only collating those terms where the first element maps to 1. Okay, maybe there are no such terms, or maybe 1 is not in the range or whatever, then you don't have this guy. Okay, and that's fine. I'm just saying that I'm collecting all those terms where the first guy maps to 1, collecting those terms where the first guy maps to 2, and so on. Here I'm collecting all the first terms that map to k. Okay, and here of course I'm looking at this particular space of functions. Okay, this function is the collection of all those functions from k to x where L of 1 is equal to whatever. At the ith row, L of 1 is equal to I. Okay, it's possible that this is an empty set, in which case you don't have those terms. That's fine. Okay, I'm just expanding out this polynomial a little bit. That's all.
That's why the index is that's what we were saying. The ith sum, it will be from k minus I to x.
Yes,
Because we have already decided that the
Yeah,
ith
whatever.
sum is
fine.
Whatever, yeah, sure. I'm saying look at the space of all functions that map k to x where the first element is mapped to I. That automatically restricts. I mean, it's the same thing. Yeah, sure. I mean, considering the domain and range are interchanged, this is a less serious typo. Okay? Is this rewriting clear? Okay? I've just clubbed similar terms. Okay? I've just clubbed the terms where the leading element here is the same. Okay? And now I'm going to reclub them. So this is the leading element. So what's this? I mean, I just sum all the y vik's. Okay? I put them together here. And of course, now here this is correct. I mean, you're only concerned with x because you were only mapping into x, right? All the remaining terms don't exist. I mean, all the remaining rows don't exist. Okay, all right. So that's what we are doing here. And now this is what we said. I mean, if you're looking at walks starting at v of length d, you can think of it as the union of walks of length d minus 1 starting at a neighbor of v, right? It's exactly the same set. So let's split this out into walks. So now you can sum over all u and n of v, and now I've renamed the variables v1 to vd minus 1, where v1 is now u. Okay, and this guy, okay, I mean this guy is the old v1. Imagine this is fixed at this constant v, right? Because we had a fixed vertex v, right? So y v1 in this old setting was v, right? So y v1 t, this guy is now a constant. Oops, sorry, it's an unnecessary black box. Here y v1 t is a constant that you can pull out. It doesn't depend on the walk anymore, right? This sum, what are we looking at here? Here v1 was fixed at v, right? And you're summing over x and you have some allocation. Okay, these are all a bunch of variables that we are looking at now, which would have some assignment. Like Saket said, all these variables have been assigned some numbers from the field. I can literally pull this out and compute it, okay, and store the corresponding number.
Then you should be summing over L which starts 1 to.
Yeah, that's right. So at every stage, okay, I've not written this out very well, but at every stage, just consider the restricted space of functions that you're left with once you have fixed some things right in the beginning. Okay, so here just think of this as a fuzzy thing, okay, which you can substitute with whatever is the correct thing. Okay, so here, here for example, you know, when you do the DP again, you'll be looking at what u maps to. U is the first vertex, and so on and so forth.
Basically, you'll have extra dimension for maps also.
Sure. You're looking, the sum is defined over a particular set of functions which you keep track of. You keep track of what are the functions that you're left with, right?
Yeah.
Okay, all right. So now I've pulled this out. This is a constant. Here also, v12 was like, what is v12? It's the first edge. It's the first edge on the walk. And I'm now splitting up the walks in this particular fashion, right? I'm splitting up the walks as from v to a particular u, okay? From v to a particular u. So this particular edge is going to be what? So this is, okay, there is some relabeling that's going on here. The new v1 is u, right? And this v1 was v to begin with, right?
2 is u.
Yeah, so this guy is essentially the edge going from v to u, okay, which also is now something that you can pull out. It's a specific guy that you can pull out. So now these are the two constants that I can pull out. I can rearrange the sum. This guy goes inside, and now this should look familiar. So notice that these two guys are now, this is the variable, this is just y v comma t. The next guy is just x v comma u. Okay, so these are these two guys out here. Again, you've given me some evaluation. This is a sum that I can compute. This is a sum that I can compute. These two guys are just constants. Okay. U is,
Second.
okay, yeah, maybe this should,
U is the
Yeah.
second vertex in the walk.
right, U is the second vertex in the walk. Yeah, that should be in here, sorry. It shouldn't matter ideally. I mean, no, okay, I mean you can just sum this over all U, yeah. I mean, sum it over all U in the neighborhood of V. Right. So now, I mean, this sum is over all walks that, I mean, so for all choices of U in the neighborhood of V, all walks of length D minus 1, right? So you're summing over all, so now there's an additional layer of sum because you're doing it for all neighbors of V as well. No, so imagine, so this is, I mean, the notation here is just tied into the indexing here, okay?
So there
Yeah.
should be a summation, right?
Yeah,
Which is a neighbor of V.
that's right. So this guy, these constants x1, 2 are also getting summed over all the neighbors of V. Okay, just like these guys are getting summed over everything in X. Okay, but whatever you do, these guys turn out to be some fixed constants based on your evaluation. Here you're dealing with all the edges going out of V. Here you're dealing with all the particular labelings that you get from V to T. I mean, whatever labels the vertex V is getting. Okay, but now what is this term? Can you recognize this term?
It is V1 D minus 1.
Yeah, exactly. This is what you've stored in your DP table, right? This is the set of all walks of length D minus 1 starting at U for a fixed U. So you're going to just sum over U and appeal to these values in the DP table. Okay. All right, I mean this is slightly overloaded in terms of detail. It is just a bit of a computation, okay? Yeah. So you sum this over, yeah. Correct. You sum it over all neighbors of V. Right, but if you expand it out, you can pull out the parts that are the constant allocations, pull it out and then multiply it with the rest. Okay. I think it's easier to do if you just take a piece of paper and a pen and write it out. Okay. All right. But okay, I mean, I'm hoping that beyond all the detail, the high level picture is that at the heart of the matter, it's still the Hamiltonian path DP, the really basic DP, which says when you're trying to count walks or paths of length D or length K, you start off by identifying a start vertex and then looking at all the neighbors and appealing to the rest of the DP table for whatever remains. Okay. So when we did the semantics of PVD, I think it's written down somewhere here. The sum was over the space of walks of length D starting at a vertex V. Okay, and now it's this space that you want to split into something that's simpler to understand, and that for which you can just call the DP table, call the pre-computed DP table how many ever times. Okay, so it's really what's below the summation that you need to get a handle over. What's inside the summation is a bunch of symbols that you need to play around with and ensure that you can pull out some things and preserve some things so that you can get something in the form that you want. Okay, that's essentially all that's happening here. And of course, there were at the high level there were two steps. You had to go from so in the beginning we had this big sum. We started with all walks and then there was all bijections. Okay, which looked quite crazy. Okay, I mean there is no obvious way of evaluating a polynomial this big. So to make things easier, we first applied inclusion exclusion, and this sum, which was over all bijections, we managed to split this into something that was over all subsets and then over some restricted bijections. Okay, bijections that mapped to only a subset of the range. Okay, now this guy we keep fixed and these two we interchange, and then after the interchanging the walks in these guys collide, and you can actually solve this using dynamic programming that's simple at its heart, really. I mean it's really the old DP for path, but of course you have to work out the details, and this was just to give you a glimpse of what the details look like. Okay. All right. So this completes the story for a randomized 2 to the k algorithm for k path. The randomization, of course, comes from the Schwartz-Zippel lemma. And okay, let's see, how much time do I have left? It's depending on that I want to proceed. We started when? 10:30?
7 minutes.
7 minutes. Okay. All right. Take it as a nice exercise that
What's the degree of this polynomial? I mean, Schwartz-Zippel lemma requires two things. The degree of it. Sorry? Okay. So
because you're
Every
multiplying.
monomial has how many terms? Like 2k terms, right?
Okay, the field size is 2.
The field size is not 2. The field size is
But we were working on a, so that's,
The-
you are going into a bigger field now.
But then I still have characteristic to it.
so there are, yeah, the important thing is that there are finite fields of.
Field, finite size
Take any
field.
extension of the
Any extension.
Extension of Z2.
Yes.
Yes. So all the details need to be set up, but it's not very clear how you can apply Schwartz-Zippel. Is that standard?
Okay, maybe not. So, all right, I can eat into some more of my time. So thank you. Anyway, so the point being made up here is that it's important to note that you're evaluating this over a field of characteristic 2. Okay, we needed that for all the proofs of correctness. Okay, now to be able to apply Schwartz-Zippel, you need to be able to sample from a sufficiently large field, right? From a sufficiently large field. Okay, but in the interests of computational tractability, you can't allow your field to be too large. Okay, so a nice midpoint is that there are, let's just say you can work with, I think the exact number is a little bit different if you want to work out the specific details of what the probability of success is, but roughly speaking, if you work with a field of size log k, it turns out to be good enough for computation, it turns out to be good enough for Schwartz-Zippel. Okay,
No, 2k, if the degree is 2k, log k is not enough.
isn't it log?
It should be bigger than 2k.
No, but
You need a field of size to power L, where L is at least 2 log.
okay, sorry, yeah, I made that mistake. 2 to the power, let's just say ordered log k, at least 2 log k. Yeah, sorry. Sure. So what is this? Like something like k square. But no, 1 second. We talked about evaluating these numbers, right? Then, oh, because you need log k
Because
bits.
then you
Okay,
basically
sure.
have a success probability of 2k by
Sure.
k square.
Sure.
So it's 2 by 2.
Yeah, that's right. So let's just say probability of success is. So what's the degree of this polynomial? The monomials that we listed? Yeah, I mean we had one variable for every edge in the path or every edge in the walk. We had one variable for every, well, labeled vertex in the path. So totally we had 2k. So the degree of the polynomial is roughly 2k. And then if you evaluate this over a field of size k squared, let's say you get success probability at least 1 over k. This is what Schwartz-Zippel gives you. Okay, this is the size of the field. And
success, that is the probability of failure.
In a failure.
oh, right. Of course. Right. Sure. Sorry. The probability that you report incorrectly is at most this. Sorry. So that's right. So that's Schwartz-Zippel in general. I think. Yeah. Right. So the probability that your polynomial evaluates to 0, right? The probability that your polynomial evaluates to 0 on a random assignment, okay, is at most the degree of the polynomial divided by the size of the field that you're sampling from. Okay, that's the statement of the Schwartz-Zippel lemma. So you plug in a sufficiently large field, okay, and the degree of our polynomial is 2k, so you ensure probability of success at least 1 over k. Okay, and you just need to work with something like log k bits to represent the elements of the field, and therefore when you multiply things out and store things at intermediate stages, you're still okay. Okay. All right, so the exercise is as follows. Okay, it's probably, I don't know, it's probably a reading exercise once you get the notes. if you restrict yourself to undirected graphs, which was a comment that kept coming up, can you take somehow some advantage of the fact that you have edges oriented in both directions? Can you actually get some mileage out of that? And in particular, if you restrict yourself to bipartite undirected graphs, which is working over all subsets of K, which was really the number of labels that we were using. That's where everything was coming from. Okay? So the question is, what are the situations in which you can maybe get away with using lesser number of labels? For bipartite graphs, it turns out that it happens to be one such situation. One of the sides of the bipartite graphs will have size at most, let's say n by 2. Actually, that doesn't even matter. Any path of length k must zigzag across the bipartite graph, right? So it's going to be roughly k by 2 guys here and roughly k by 2 guys here. So can you somehow smartly use only k by 2 labels to preserve the semantics of this path? Okay. First of all, the basic idea is to try and only focus on the vertices that intersect with V1 and somehow patch with, let's say, the bipartitions are V1 and V2, and you want to, let's say, only distinguish the vertices on one side. Okay. And so use k by 2 labels to talk about the vertices on one side, and somehow because of the bipartiteness can you get some control of what's going on the other side. And really the only thing that you need to work out is that for the same sort of polynomial, I mean just try to build the natural polynomial with a smaller labeling function. How do you make sure that walks actually cancel? Okay, you may have, with a more restricted labeling, it may not be obvious that walks actually cancel. So just fiddle around with it, not necessarily to get to a complete solution, but to get more of a feeling for what this kind of encoding is. Okay, I mean I need it as well, so we can discuss this offline if you like.
Just
so
say, even things will only go to even. I mean, like the permutations in a walk.
Right.
So what we want is when we swap two things, when say a vertex repeats, we want these two to have
correct.
the same.
Correct.
So we know that a vertex repeating
will be on one side.
Distance.
Correct.
Just take permutations in which.
Okay, if you go correct, if you
It just reduces your thing by half.
that's right, but that's like a fancy class of permutation. Correct. That's like, but okay, I mean probably works. I mean just the immediate issue is that you'll have to redo the entire computation if you're working with a fancier space of permutations. Exactly. You use the permutations over k by 2. Try to get away with labeling only half the vertices. And correct. So what will happen is if the path is repeated vertices on the side that you are labeling, you are fine. But if the repetitions happen on the side that's unlabeled, then you still have to make sure. No, but then paths might cancel. But how is it the same labeling if you're using A1 and B1?
It's just to distinguish between this vertex from this partition, this vertex from other partition.
But then you're still using.
Because you have the same labeling. No, it will be A1, A1, A2, A2.
No, I'm saying A1, B1.
But then it's different labels.
So A1 has to name the vertex A1 and have a labeling as A1, 1.
Uh,
But then even then, what is distinguishing this path and this?
So the path will be like A1, I mean, the path will be A1 to B1, then B2 and
Now the mirror image also is the same.
no, I'm saying that labels will be different, right? A1, 1, B1, B2.
But that's
You can't distinguish between the labels, right? That's so here again we have B1, B2, B3, B4, B3.
okay, you have a lot of things to check. You have to make sure that seriously every walk cancels somehow, and at the same time you have to make sure that you don't accidentally make paths cancel. Okay. So
What detection of how much?
sorry.
What are we aiming for?
You're aiming for, let's say, just using k by 2 labels in the same framework. Let's make this easy. Let's say that the second half of the entire framework stays exactly the same. So you just want to deal with somehow permutations over a smaller space. But now the smartness will be in how you use those permutations and labeling the vertices. What's the monomials that you come up with? And once you fix the polynomial, the rest of the machinery, of course, has to be adjusted, but is essentially the same. Okay? All right. The size of the DP table, it should work out to polynomial. For every vertex, for every vertex you're only looking out at its neighbors and moving on. Yeah. This is a lot like the, I don't know if you've seen branching walks, it's like that too. So. Okay, I think on that happy note we will stop. And I think we have a coffee break, and we will be back. In the next lecture, we will see how to do some algebraic mess inside 3D compositions. So that should be fun. Okay? All right, so see you around.